Picking up where we left off on the quiz, question 9 asks you to write a function that fits the function f of x equals x squared minus 5x plus 2 at the point x equals 1. They could ask you to write a linear approximation. They could ask you to write the equation of a tangent line and make an estimation using a tangent line, various ways of doing this. So the most basic way to do this is just to say I'm going to write the equation of a point-slope form line. That's y minus y1 is equal to m times x minus x1. You can use the tweaked version of that formula, which would be basically to solve for y, and you would have y1 plus m times x minus x1. Your book uses a little different notation. They say that L of x, actually C I think is the point that they're doing it at, is equal to the initial value of the function at c plus the slope, which of course is the derivative at c, times x minus the initial value of x. You can do that sort of thing. So anyway, you'll see a couple of options on here. Actually, a lot of times this is written as dx because this just ends up being the change in x between your 2 points. So anyway, a bunch of different ways that you can write this. Our original function was f of x equals x squared minus 5x plus 2. And we want a function that fits that at x equals 1. So when x is equal to 1, y is equal to, let's see, 1 squared minus 5 times 1 is negative 4 plus 2. Looks like y would be negative 2. We need the point that it passes through, and we need the slope. The slope, of course, is going to come from the derivative, which is 2x minus 5. We want the slope at x equals 1. 2 times 1 minus 5 is equal to negative 3. So basically, we just fill everything in here. Our x-coordinate here is 1. Our y-coordinate is negative 2, and our slope is negative 3. And so you get several different versions of equations. You get y plus 2 is equal to negative 3 times the quantity x minus 1. You might want to solve for y equals 2 minus 3 times the quantity x minus 1. You might see something kind of like that. And again, it's the same thing. If you used this formula here, you'd have the initial value. That would be the value at f of 1, which was that y value of negative 2. Let's see, negative 2. Oh, I'm sorry. This should be a negative 2 right here. You subtracted the 2 from both sides. Anyway, so yeah, you'd have that negative 2 there, and then you'd have the derivative there, which is negative 3, and then you'd have your change in x, which is going to be x minus 1. So that's basically what's going on. Anyway, in this particular case, it asks us to estimate f of x equaling 1.1. So we can put a 1.1 in here, okay? The change in x, by the way, delta x or dx is just going to be 0.1, right? Because we're going from 1 to 0.1. So basically this is delta x or dx. 1.1 minus 1 is 0.1. If your change in x is 0.1 and your slope is negative 3, you would expect to drop by negative 0.3. So that would give us negative 2.3 as our estimate, okay? So anyway, the error here, I believe the actual value is negative 2.29. So to find the error, you take the actual minus the approximate. And anyway, if you subtract the approximate there, you're going to end up getting positive 0.01, which just basically means if you add 0.01 to the estimate, you're going to get the actual value is what the error would be. Or you could say that it's 0.01 below the actual value, something like that, okay? Part C asks us for the values of delta x, dx, delta y, and dy, and we can figure all those out. We were starting at an x of 1, moving to a point of 0.1, so that would be 0.1, that would be 0.1. Remember, delta y is the change in the actual function, so that is the actual f of 1.1 minus the estimated f of 1.1, which in this case is negative 2.3. And anyway, I believe the actual change in y, I believe it was actually negative -0.29, I think, and the estimated decrease was -0.3, and that's your dy on, that's your change in y on the linear line. So anyway, that's what was going on in number 9. Question number 10 says the surface area of a sphere is calculated using the equation A is equal to 4 pi r squared. They're asking you to find the equation for dA. Remember that dy is just equal to the derivative times dx, okay? Or you can take the slope times the change in x, and that'll tell you the estimated change in y if you had a linear function. So this is really the same thing. We're just using an a variable and an r variable instead. So the derivative of a you would write as dA. The derivative of 4 pi r squared would be 8 pi r, and then you're multiplying by the change in x, or in this case, I guess your x variables and r variables, so you'd be multiplying by dr. So it's just the derivative times the change in the input variable. That's your dA statement. And if you wanted to estimate a change in the area, let's say that they gave you the surface area when the radius was 4, and you wanted to estimate the surface area when the radius was 4.1, you just fill in your original radius of 4, and that would tell you the slope of this, basically the rate of increase when the radius is 4, and just multiply it by the change in the radius. So if you wanted to go from a radius of 4 to 4.1, you could make that 0.1, you could make that 4. That would give you the estimated change in the area, and you could add that to the surface area when the radius was 4, and that would give you an estimate of what the radius would be, what the surface area would be when the radius is 4.1. Okay, is that necessary? No, since we have the formula, it's not necessary, but that's how the concept works. All right, so number 11 says given function f such that f of 3 is 6 and f prime of 3 is equal to 1/2. Worded badly there, but it asks you to find a linear approximation for f of 3.2. Okay, so we know it goes through the point 3,6, and we know that the derivative at that point is 1/2. Okay, and anyway, so visually on a graph, what's happening is you're at this point 3,6, and we just basically want to extend out to this next point here. And remember, we've got this idea that the change in y is equal to the slope times the change in x. Okay, the slope is the derivative, in this case the derivative at 3. So the derivative at 3 is 1/2. The change in x, we're starting at 3, we want to estimate 3.2, so our change in x is going to be 0.2. Okay, half of 0.2 gives us an estimated change of 0.1. Okay, so we don't expect our function to go up by 0.1 from that point to the next. So the function was at 6, it's going to go to 6.1. Now you can do this the long way. You can use a point slope form of the equation, and you'll get the same thing, just more work. The easy idea is to take the slope multiplied by the change in x, and that tells you your estimated change in y. But you can say y is 6 and x is 3, and my derivative is 1/2. That's my slope. So I have y minus 6 is equal to 1/2 the quantity. Sorry, x1 is 3. X minus 3. And you might want to solve for y. Do 6 plus 1/2 times x minus 3. And then you can put in 3.2. But look, the same thing is going to happen, right? There's your initial value of y. You're taking the slope and you're multiplying it. 3.2 minus 3 is just 0.2. That's the slope times the change in x is what you get for this value right here. So 6 plus 1/2 times 0.2 is just going to equal 6.1, and that's your estimated value. So various ways of doing it, but that's one way of looking at it. All right? All right. Riemann Sum Question should be one of the easier problems on the quiz. Not necessarily one of the fastest ones, though, so I do have a feeling some people kind of waited on this one. We're looking at the interval between 4 and 6, and they want 4 rectangles, so hopefully you figured out the interval is 2 units long, which means each of these rectangles, to get 4 of them, each rectangle is going to have to be 0.5 units wide. So we're going to have 4, 4.5, we're going to have 5, 5.5, and then 6. Now, they want midpoint rectangles. So if it was right sums, you'd be picking 4.5 as the height of this, and f of 5 is the height of that, and f of 5.5 is the height of that one. Midpoint, we're going halfway between these two. It's whatever the value of f of 2.5 is right there, and then halfway between these, that's whatever the value of f of 4.75 is, okay? And the midpoint here, that's going to be whatever the value of f of 5.25 is. And then this point here, that's going to be whatever the value of f of 5.75 is, okay? So anyway, if you draw these in, you know, that's what your rectangles would look like. And you can see as you get toward the top, these are getting pretty accurate. So each rectangle, the first rectangle, its width is a half, and you're going to be taking a half times whatever that functional value there is. Okay, for your next rectangle, its width is a half times whatever the height is, which is f of 4.75. And then the next rectangle has a width of a half times f of 5.25. And then finally you have 1/2 times f of 5.75. And that's the work that you need to show. At that point, they don't really care where you come up with your answer. But anyway, I would suggest sticking this in a graphing calculator. Let's see, our function here is radical x. And you can make a table, because everything's spaced out so nicely, you can start this at 4.25, and you can make your scale go by 0.5 and go run a table. And again, you want a lot of digits here. So, so anyway, f of 4.25 looks like we're taking 1/2 times about 2.06155, and again, you may want to keep these in your calculator even if you can. Then you're taking a half times f of 4.75, which is about 2.179449, plus 1/2 times f of 5.25, which is going to be about 2.29129, and then 1/2 times f of 5.75, which is going to be about 2.3979, something like that. And anyway, you can add all this up and you can get your estimate. So it's quick. By the way, you may want to factor those halves out and just add all this up. So 2.06155 plus 2.1799449 plus 2.29129 plus 2.3979. And I'm going to take half of all that. And so it looks like we're getting approximately 4.465 when we round to 3 decimal places. So you notice I went several places past 3 to make sure my accuracy was correct. Okay, and we move on to number 13. Number 13 was a mean value theorem. Remember, the mean value theorem basically just says that if you have a function that's continuous and differentiable on an interval, there should be some place in the interval where the average rate of change equals the instantaneous rate of change. In other words, the slope of the tangent line is equal to the slope of the secant line. And of course, the average rate of change is f of b minus f of a all over b minus a, just the slope from the start to the end. And we're saying it's got to equal the derivative somewhere, and we're trying to figure out where it equals the derivative. So basically doing an average rate of change and a derivative and seeing where they're equal. So anyway, the average rate of change here, in this particular case, that's going to be f of 3 minus f of negative 3 all over 3 minus negative 3. Let's see, f of 3 here in my original function, 3 cubed minus 3 times 3 squared, is that 0? That's interesting. And then if I put negative 3 in there, that's going to be negative 27 plus, let's see, 27, wait a second. Second guessing myself here. Real quickly here, just to make sure I get this right, let's stick this in the calculator. And okay, I want this at count by 3s here. Okay, so f of 3 really is 0. F of negative 3 is negative 54. So it's going to be 0 minus 54. Okay, and on the bottom we have 6. 54 over 6 is equal to 9, okay? So the slope from the starting point to the ending point was 9, okay? So like in this, if it looked like this, which it probably doesn't, our slope would be 9. And we want to figure out where is the slope 9? Where is the derivative equal to 9? So we're going to go back to our function. I need the derivative, and I want to set that equal to 9. So the derivative is going to be 3x squared minus 6x. And I want to set that derivative equal to 9. So we've got 3x squared minus 6x minus 9 equals 0. You could go to the quadratic formula here. I'm going to factor out a 3. and that's going to give us x squared minus 2x minus 3, and I think that's going to factor. So 3 times the quantity x minus 3 times quantity x plus 1 is equal to 0. And so we're going to get solutions of 3 and negative 1. Well, that's interesting. 3 is actually not in the interval. It actually guarantees values in the interval, not including the endpoints. So that's interesting. Technically, 3 is not guaranteed by the mean value theorem, although it does work. But anyway, technically just negative 1. I think I actually accepted 3 and negative 1. I wanted you to show me algebraically that there were 2 possible solutions, even if one of them technically isn't inside that interval. So you may get extra answers that you know, aren't required. All right, let's look at these definite integral problems. We've got the definite integral from 1 to 4 of 3x squared minus 4x dx. And we've got the definite integral from 0 to pi of sine of x dx. Okay, so we're going to come over here. Remember, the fundamental theorem says if you're trying to find a definite integral, you can take the antiderivative, so that's x cubed minus 2x squared, and you can substitute the 2 values into the antiderivative and subtract. So sometimes we call this antiderivative big F. We could take big F of 4 minus big F of 1. That's going to be 4 cubed minus 2 times 4 squared. And then we're going to sub 1 in there. That's going to be 1 cubed minus 2 times 1 squared. Okay, let's see, that's going to be 64 minus 32. Is that 32, I think? And then we're subtracting, let's see, 1 minus 2 is negative 1 minus negative 1. Looks like 33 there, if my arithmetic's correct. Yeah, might want to check that. And on the second one, the antiderivative of sine, the derivative of negative cosine of x is positive sine. We're evaluating that between 0 and pi. So negative cosine of pi minus, and be careful, it's minus negative cosine of 0. Let's see, the cosine function at pi, cosine function at 0 starts out at 1. It's going to hit negative 1 there, so it's a negative 1. Cosine of 0 is 1. Minus a negative is a plus. So we get negative 1, which is 1, plus 1, which is equal to 2. And by the way, that is fascinating. It tells you that the area under one curve of the sine function between 0 and pi is exactly the whole number 2 units. Crazy, huh?